The next speaker in our agenda is Owen O'Driscoll. Dr. Owen O'Driscoll is a graduate of Trinity College Dublin, Ireland, with a mechanical engineering PhD, a Bachelor of Science Engineering with Management, and a postgraduate diploma in statistics. Owen's specific areas of expertise are energy management, building automation, optimization, and smart building implementations. Owen is a licensed professional engineer in the Commonwealth of Virginia and an AEE certified manager. Owen has developed and implemented multi-million-dollar facility optimization projects across many industry verticals to enhance energy performance and create more resilient critical environments. Owen is currently authoring a book of Elsevier Publishing titled Smart and Resilient Buildings, a Data-Driven Future. So without further ado, on to you, Owen. Feel free to start presenting.
Thank you, Kritika, and good morning, everybody. So this morning, I'm going to be speaking about some of the ways that smart buildings can save money. And so far, at least in my opinion, the presentations have been really interesting. It seems like there's, I think, a lot of cause for optimism after the economic outlooks that we've seen, but there's still uncertainty, and I guess it's really extra uncertainty about what the future holds as we try and rebound from the pandemic. So I think what I'm going to say before we get started is this presentation is going to be a little different than what's come before. And I'm going to be focusing on the intersection sort of between engineering and statistics and how improving how the buildings we work in operate can save money and even generate revenue in some instances. So one obvious point, as everyone's talking about COVID so far this morning, or it's been touched on in multiple talks, is the buildings that we work in are changing, and a lot of us don't work in buildings anymore. And in the future, maybe we will, maybe we won't. I personally don't think that it's going to go back to the same working environment as we had before. But even in that fact, there's a major and maybe even an obvious cost-saving opportunity in smartly reducing the amount of leased and owned office space that organizations have. And we'll get to all of that a little bit later on. So as Kritika said, my background is in that intersection where smart building sits between mechanical engineering and statistics. And I've spent the last 8 years or so working all across Virginia in lots of different places, making buildings and campuses of buildings more resilient, more efficient, and less expensive to operate. And as Kritika said, I am from Dublin, Ireland, and one of the most serendipitous things, I guess, that happened to me when I moved over to the US was the first site I visited was the Volvo trucks plant in Dublin, Virginia, when I moved over to the US. So just I guess a funny tie in there to my own personal background. And it's not a lot of manufacturing work. Most of the work that we're doing and that I've done in the past does focus on multi-building campuses, schools, a lot of work at Virginia Tech, UVA, the community colleges, NVCC, most specifically, and I'll talk to some of those stories over the next little bit of time too. All right, so what am I going to talk about? The first thing I'm going to try and do is define what a smart building is. We'll talk about some of the benefits and challenges associated with smart buildings. And then the most important piece is the underlying foundation of a smart building. So data is key, and I'll talk about that. And most of the presentation then is going to be practical examples of smart buildings in action. And understanding, or at least trying to understand the audience here, what I'm going to try and do here is tie the cost benefits, I guess labor efficiency is included there too, to each of these examples. So outage management, how smart buildings respond to flooding, and some other examples. And then lastly, looking at how smart buildings are also safer buildings. So we're talking about people going back to the office. Well, what does a smart building do to make that office, or really any end use interior environment, more safe? So we'll talk about that too, and then hopefully we've got some time for questions at the end. All right, so the first thing I'm going to do is define a smart building. And that's a little bit easier said than done because there are lots of conflicting definitions out there. And I think a lot of people use smart, intelligent, and even autonomous buildings interchangeably when in fact they're quite different things. So in the context of this presentation, the headspace that we're all going to try and get in right now is that a smart building is one that leverages data to holistically optimize performance. So broad definition, but I think that sort of keeps it safe. And the key to any smart building is data. And a smart building is fundamentally dependent on a platform that's able to collect and compile data from different existing building systems and then analyze that data in real time. So there's lots of different systems that exist in buildings, and we'll get to some of those. But the key is the smart building has to have a sort of brain, we can call it, a platform that can collect all that data, process it in real time, and then let people know or automatically make changes to improve operation. So that means we're connecting to, lighting, HVAC, but we're also connecting to utility providers. We need to understand utility grid interconnections, because now we're not just consuming power, maybe we're also providing power back to a grid. We need to have information from weather sources. So what's the weather going to be like in the next 12 hours? How can a building be prepared for what may come? Needs to be connected to public transit information. So how are people going to get to and from a smart building? And once all of that data is brought together, what you end up with, at least in theory, is a much more resilient and efficient space to operate. And I think one of the pitfalls before we get into this that people fall into is smart buildings are green buildings or sustainable buildings. And while that's true, smart buildings are much, much more than that. And the number one reason that people are beginning to invest more and more in smart building technologies is long-term cost savings. So a portion of that is reduced energy costs, reduced utility spend, but it's much, much more. It's much more than that. Extending equipment lifetimes, increasing the sort of costs to lease space, or at least the revenue that can be generated from leasing spaces. So it's much more than energy efficient, although they are very energy efficient as well. So yeah, number one benefit is that they're connected, and then the challenges to realizing smart buildings are also tied to data and the interconnection of different systems. So if we can't have a smart building unless a building connects all of its existing systems, we have to be extremely cognizant of cybersecurity. And just from, keeping even a soft eye on the news in the last couple of years, the prevalence of cybersecurity incidents, or at least how often they're being reported, is increasing dramatically. So it's very important that the systems are integrated in a cybersecure way. And then as we bring the data together, we end up with a lot of data. Okay, so you're talking about millions of data points every hour, and it's hard to process that data and sort of transform it into information, into intelligence, into decision support, knowledge that can help people make changes. And that's another challenge with smart buildings. Sometimes the data all comes together and there's very little value derived from it, and then it just becomes sort of a wasted project, and we obviously don't want that. So the first thing, and what I'm going to talk about on the next slide, is the data infrastructure for a smart building. Okay, so this is like a conceptual diagram, I guess, and I'm going to walk through it. And I know it's not mostly engineers on this call, so I am going to keep it just describe roughly what's happening. And if people have questions, of course, I'm happy to answer. But on the left-hand side, what we have is the systems that exist in buildings. These are not new systems. These are the systems that almost every large building, being something over 100,000 square feet, they'll have. So we've got building automation systems, we've got meters. I think more frequently now there's electric vehicle charging stations, and then we have some other utility and emergency power systems. Most important thing to notice or take from the left-hand side column is that they're individually functional systems. So a building automation system controls HVAC, and it does a pretty good job at it. Battery storage, it does exactly what it says. If you want to use battery, it's there and it's functional. But what they don't do is they don't communicate with each other, and they operate completely independently. So they're siloed systems, and there are lots of different reasons why that's the case. And I think one good example of a cause there is that when you think about building automation, there has always been 5 or 6 main vendors. You know, everybody sees the logos on the trucks that drive around, and I've worked at more than one of them, but they have proprietary communication protocols, and that's initially because of security, but it's also maybe, you know, to help not lock in, there's certainly a better word than lock in, but to help customers sort of stay with that one vendor. But that's all changed in the last, say, 15 years or so with open protocols. So now people are maybe getting a little bit smarter themselves, and they want to have many options instead of just one. So now everyone is starting to use open protocols, and open protocols are a huge enabler of smart buildings. Okay, so that's the left-hand side. On the right-hand side, we have some of the outcomes that a smart building can help deliver. Okay, so what does a smart building do? Well, it makes indoor air quality a little bit higher, or a lot higher. It performs predictive optimization, so it's going to tell you what you need to do before you need to do it. So let's say you're looking at weather forecast data, and it's going to get really warm in the next 6 hours. It's going to get very humid. It will tell you that you need to increase your cooling capacity. So maybe now is the time to turn on an additional chilled water pump or a chiller itself. So it's helping you do what you need to do before you need to do it. Condition-based maintenance is another application, and we're going to come back to that a little bit later on. So a lot of maintenance practices are time-based or calendar-based, and we all sort of fall into this at home. You change the filter in your air conditioning unit every 3 months because it's a recurring alert that you have on your calendar, or at least that's what I do. But that's not always wise, because sometimes you're changing a clean filter, okay? But you just do it because that's the schedule. So using data and sort of smart building philosophies, you start to monitor how the filter is actually performing, and then it will tell you when it needs to be changed. And that's a way to, you know, have a more efficient maintenance operation, which in turn is a much more efficient facilities management operation. So that's where we want to get to. And then the whole middle piece, the message there is just, that is the brain. So I said brain beforehand, and that's what we're looking at in the middle. So we need a way to integrate all of that data. So all of those little circles just have different protocols, different languages. We're bringing the data into one place, and then we have analytics, alerts, notifications, and that's how we bridge the existing systems with the applications of a smart building. So like I said, very conceptual, but that's the thinking behind a smart building from not 50,000 feet, maybe 10,000 feet. So that's what a smart building is. And that's all the intro we need. And now what I'm going to do is talk about some actual examples of smart buildings and smart campuses in action, and then try and quantify some of the savings that result from doing things a little bit smarter. Okay, so the first one is related to a power outage that happened in the DMV a few years ago. So chunks of DC, Maryland, Virginia lost power because of something that happened in Maryland, actually. And there's nothing especially interesting about this one outage, but I just want to use it because it's a good story to tie in the sort of smart example I'm going to speak to. So what happened is the power went out, and there's a line in this Washington Post article that says, in most cases, the lights stayed on because backup generators kicked in. So that's, you know, however many words that is, 7 or 8 words. But there's a tremendous amount of work to characterizing and establishing what actually happens on a campus when the power goes out. So when you lose grid power, not surprisingly, what happens is there's an outage, lights go off. But this is an eventuality that's planned for, it's designed for. If you work in a federal or a state building, you've got emergency generators. A lot of people even have emergency generators at their homes. But what actually occurs when the grid power is lost is that a physical switch will move, and it changes the circuit. So now your building isn't fed from the grid anymore, it's fed from an emergency power circuit. But if you have a large building or a large campus of buildings, there could be hundreds or maybe even thousands of these switches, and that the location of the switches, if they successfully switch or don't, isn't a stream of data that finds its way to a dashboard. They're just switches that switch. They're switches that switch as soon as the power is lost from the grid, and it should go one way, but it doesn't always. Then when the grid power comes back on, it should go the other way again, but it doesn't always. So what happens is you have incident response groups who have to physically go and look at the switch locations and make sure that they're doing what they're supposed to do. So the example I'm going to speak to is for University of Maryland, and that's why that's underlined, because this is exactly what happened during that outage. The grid goes down, power's out for about 45 minutes, but the campus is forced to close for 6-7 hours because they can't respond the way they need to because they don't have access to the data. They don't have access to the data because it's not integrated, it's not smart, and they're relying on a manual process. The manual process is people going to look at switches and then calling back into an operations center to let people know what's happening at each location. And purely because of this outage, and I guess outages like it, they changed how they respond to outages. And I'm going to show a screen for the University of Maryland, but this is something that's being done at Virginia Tech and lots of other multi-building campuses across Virginia. So Maryland just works because I guess it's tied to this news story and this outage. So that's the challenge. And then this is what it looks like now. So this is how outages are characterized at College Park right now. And this is very, very simple to look at, and that's exactly what it should be. So green is good, red is bad, and all of the data from the different buildings, from the different switches, from the different emergency generators are all brought into the brain, the smart building system, and then it's presented on a geospatial map that people can pull up on their screens, pull up on their phones, and as soon as an outage occurs, if the switches switch the way they're supposed to, it's no issue. If they don't, you get a list of exactly what buildings are experiencing an issue, and that helps with the triage process and allows you to get to remediation as quickly as possible. So completely different, right? This is like a total step change in how people respond, and this is becoming the norm. And then knowing the audience, I tried to sort of quantify the economic impact here. And the first one, maybe I shouldn't have started with this one, but I struggled with this because large university campuses, really any campus, the availability, so how often they have power is very high, 3, 4 nines, 99.9% or more over a year. But even improving availability for a campus like College Park by an hour, by 2 hours over a year is pretty significant. All right, I'm not going to put a number out there, but I would think it's in the millions of dollars range. And this is something that is purely made possible by integrating data that you're already generating. It just isn't integrated. So that's the nature of a smart building, and I think this is a really good first use case. Okay, so then the next one is, that was multi-building campus, and now it just goes right into a within a building. So this is something that persists, and you don't need to be someone who's worked in this space for 20 years to understand why it doesn't make sense. But the way scheduling of common areas in building works is that there is no connection between the systems that control HVAC in common areas. So think about classrooms, think about meeting rooms, think about auditoriums, spaces like that. There's no connection between those automation systems, and that's what I have on the right-hand side, and then the actual occupancy schedule data. So here, think about, your Outlook calendar when you book a room, or Google Calendar, or whatever cloud-hosted platform it may be. That's where professors put the English at 9 a.m., or I might put a meeting that's a review at Tuesday noon or whatever. There's no connection between that data, so what the occupants are actually planning to do, and then the systems that control the spaces. And I would say that statement I just made, that there's no connection, is true for 85% or more of, commercial office space. And the reason that it's done is because the automation system speaks a different language. The cloud hosted data hasn't previously been connected to the automation system for lots of different reasons. So the result, the sort of standard way of doing things, is what's called a global schedule. And a global schedule is, what's the worst case scenario? Worst case scenario is we've got a 6 a.m. meeting or a 10 p.m. meeting. So the schedule is we're going to condition our meeting rooms from 6 a.m. to 10 p.m. regardless of the fact that, maybe only 25 or 50% of that time the space is going to be occupied. So now, being smart, okay, connecting the data systems, what we're doing here is, and again, the bridge isn't important. The really important fact here is that there is a bridge. What we're doing is we're taking the data from the calendars and we're moving it, protocol converters, changing the language, and then we're speaking to the automation system and we're making it only provide conditioning, ventilation when the space is occupied. All right, so if you think about your own office building, you definitely have a building automation system, and you definitely have some sort of calendar tool that records how often a space is going to be used. That's how there are 4 meetings at the same time in a room, but they're almost certainly not connected. And being smart means we are connecting those, and the net result is major energy savings because we're only conditioning when there's people in the room. So then this is what that looks like. So this is my attempt to put that economic or financial spin on it. What does that mean? So this is a power profile. So just, energy consumption over time for a week, and a week when this scheduling change. So going from, less smart scheduling or no scheduling to smart scheduling. And you can immediately see that there's a big drop off in the peak demand across each of the days after this change is enacted or implemented. So looking at a building, operating costs, a standard building, it's about $2 a square foot for utility costs, and about 40% of that is HVAC. And from my experience, 25% of that or so is conservative. So you can get to 80 cents per square foot a year by connecting the two systems that you already pay for, that you already have. So just by bridging those two systems and getting smarter, that's the sort of conservative estimate of what's possible and what can be saved. So again, not rocket science, far from it. But sometimes making a building smarter is just doing something that's maybe even obvious. The simple things of connecting siloed systems. Okay, so then the next example again is, it's not rocket science either, and this is to do with flooding and the financial impacts of flooding across Virginia. I'm not an expert in ecology or the floodplains in Virginia. So this data is all taken from the National Flood Risk Assessment, and at the risk of trying to oversimplify something that's not simple, I think the sort of summary I have is that it's bad and it's getting worse. Okay, so there's a lot of flooding in Virginia. There's a lot of non-residential properties at risk from flooding events for lots of different causes. And I think the causes of flooding are also beyond the scope of this, be it climate change, land zoning, urban development. All the different causes are not for me to speak to. But the fact is that a lot of buildings are vulnerable to floods. So that's the real fact that we're trying to take away from here. But that's not new information. So the people who design buildings, the engineers and architects who design buildings, know that there is a flooding risk dependent on where the building is, changing weather patterns, et cetera, et cetera. So much like emergency power, it's designed for it. But much like emergency power, it doesn't always work. So buildings that are in flood-prone areas have sump pumps and lift stations. And I guess like emergency generators, a lot of people's homes have the same pieces of equipment, although on different scales. But what happens is those systems don't always work. So we've worked at lots of different places across Virginia and elsewhere that have major flood events, and the below grade spaces are flooded, and it's expensive to sort of renovate those spaces. But there'll be a sump pump or a lift station that was in the space and didn't operate, and that's sort of not smart. Okay, so how do we make that smarter? The way that we make that smarter is we connect the dots again. So there is a sump pump. The sump pump does tell you how it's doing. So, you know, is it available to run? Has it been run recently? Does it have a belt? You know, is it able to spin at the right RPM? You can get data out of these pumps, but most times they're just isolated. They're in, you know, mechanical basements. They're not checked on that frequently. And yet we expect them to run immediately on the once or twice or maybe more a year that we need them to run. Okay, so that's maybe not a fair expectation, and the solution is continuous monitoring. So now we pull the data from the pumps, the operational data from the pumps, and we bring it back into that brain that I've spoken about more than once, the data foundation of the smart building. And now we're continuously monitoring, and it's automatic. All right, so nobody is looking at the screen that you can see. I mean, it's there if you want to look at it, but the purpose of the screen is when something goes from good to bad, or from from available to not available, that's when we want to be alerted. That's when we want to go and look at it. And, you know, 99.99% of the time, it's going to go unavailable when there's not a immediate need for it to run. Okay, so that is condition-based maintenance, and that's smart. So trying to, I guess, quantify the impacts there, the economics again. The one school that we've been working with used to have 5 significant flood events a year, and they were estimating that each event was costing about $500,000. So by pulling the data from those sump pumps and lift stations that they already had installed, right? We're not installing new pumps. We're just taking the data from systems that we've already invested in. By bringing that to our smart building platform, they haven't had an inundation event, at least a significant one, in the last 2 or 3 years. So that's why I've got that estimate there, $2.5 million of avoided costs from remediation work associated with repairing floods. And, you know, it's the same story as we've said before. It's not new systems, it's not new equipment, it's just making better use of what is already installed. And I think that's a very simple definition of doing things smarter. And then the last example before I get to the safer reopening or smarter reopening post-COVID is more along the lines of maintenance again. And it is tied to an example that I gave previously. So the way maintenance operations work across, you know, again, 80% or more of the buildings that we all work in is calendar based. All right, so I already talked about the filter. We change it quarterly. We check, you know, drive belt tensioning twice a year. That's all calendar based. It's based on manufacturer recommendations for 100,000 of the same unit in a nominal environment, and that's where those numbers come from. But that's not how any piece of equipment operates, because it operates in your environment. It's not the average or the mean or whatever of 100,000 other pumps. It just has the environment you're operating it in. So what we need to do is we need to pull the data from that piece of equipment. So here, this is an HVAC unit, a large HVAC unit, and you can see a motor and a fan on the right-hand side. And what we're doing here is we're looking at vibration. Okay, so we need to do alignment on a belt-driven fan annually. If you look at a manufacturer journal, it would say something like that. Okay. But what we're doing now is we're looking at the vibration signal, and now the vibration signal is going to tell us when we need to do alignment, and it's normally less than a year. Okay, maybe it's 18 months, maybe it's even more. And what you're able to do with monitoring the data, and the line graph I've shown here is actually indicative of a misalignment of a fan. Two bearings of a fan shaft. So the 2 green lines, and you can see that there's a difference. There shouldn't be a difference. The difference symbolizes or signifies a misalignment. So this is a way we were able to identify a shaft that needed to be realigned outside of the schedule-based maintenance. And the impact of something like that is also hard to quantify. The one piece is there's no unscheduled downtime, but the second piece is you're making your labor force, and I think, you know, we've heard a little bit about labor force challenges, so maybe there's going to be less people. So with less people, the smart thing to do is have a more efficient labor force, and that's what we're talking about here. So now, instead of changing a filter quarterly or monthly, if we're doing that annually based on the condition of the filter, the people that we have are much more efficient, because every hour someone spends replacing a clean filter, you know, at home, at work, wherever, or tightening a belt that's, you know, at the right level of tension, that's an hour wasted, and it's an hour that's much better spent doing something else, right? It's not like that's all these people have to do. There's always backlogs, and there's 100 things, and I think, you know, it's the same for all of us. So if we could get an hour back instead of wasting an hour, that's a significant impact, and maybe one that's hard to put a dollar value to. Okay, so the next thing I wanted to do is talk about safer reopenings. So post-COVID safer reopenings. Everything I've spoken about so far is to do with, I guess, the mechanical operation of buildings. And this is going to be different. So this is how we can use data and how a smart building can become a safer building. So I think, you know, this is the first pandemic since there's been, you know, major automation systems, and there's lots of different guidance coming from lots of different bodies. And that's what I have listed on this slide. So everyone says, you know, we need better filters, we need more ventilation, and that's very high level guidance and sort of hard to operationalize. So one of the things that's happening is people are following the guidance, which, you know, makes sense. That's why it's there. And they're changing filters as one example. So a regular office building has a filter with a rating. It's a MERV scale, and they have a normal rating. Post-COVID, now there's a new filter. It's a better filter. And it makes these systems behave differently, but differently in a way that you can monitor it with data. And I'm going to get to that on the next slide. Also with ventilation. So more ventilation. It's pretty simple guidance, you know, more air, better filters, less dust, and any other contaminants or whatever in the air stream. But a smart building can give you much more granular information. So now what I'm going to show is what that looks like. So for air filtration, the CDC says we need to go from MERV 7 or 8, and MERV stands for minimum efficiency reporting value. So it's something specific to filters. So a MERV 7 filter isn't as good a filter as a MERV 13 filter. And that's the change. So they say go from a 7 or an 8 to a 13. With condition-based maintenance, and stick with me on this one. So with condition-based maintenance, what we used to do, the old way of doing things, was we would measure pressure drop across a filter. Okay, so pressure drop, basically it means as a filter gets dirtier, there's a higher pressure drop. At some point, there gets to a pressure drop level that isn't good, and then we say we need to change that filter. That's the way it's been done in smart buildings for however long smart buildings are around. But in a post-COVID environment, it's different. So now we sort of reverse that analysis. So now we have a better filter, there's more pressure drop, but what we're looking to do now is make sure that we have a filter in place. Sometimes filters can be dislodged. You'll get a lot of air bypassing around filters if they're not installed the right way. So now, instead of monitoring the pressure drop, seeing when it increases to a level, and then alerting to change the filter, now we're monitoring that same pressure drop value, but if it decreases, then we know that there's an issue, because maybe the filter isn't there, and that means that our indoor air quality is going to be sort of less safe, we'll call it, in this environment. So that's a new way of looking at the same data, and again, it is a smarter way, and in this case, smart is translating into safe and not into, you know, less expensive. So that's one example, and then the last one I wanted to give is to do with the rationalization of space. So I can only speak for DSA, and I know in the post-COVID working environment, the amount of office space that we have as an organization is going to be less after COVID than it was before COVID. I think that's something that I think most people can agree with. But just saying that we need less space is an imperfect way of quantifying how much less space that you need. I think one of the things that we've had more than once is surveys. So do you want to work in an office? Do you want to have your own cube? Do you want to have a hotel space? And I know, just speaking for myself, when I answer those questions, I answered the way I think I'll behave or I want to behave. So maybe I'll say a cube would be great. But the reality is that's just what I'm thinking when I fill out that survey. So again, it's an imperfect way of figuring out how a space is actually being used or how a space will be used. But there is an answer with data. So what you can see on the left-hand side of this slide is an occupancy tracking map. So this shows you how a space is used over time. So you can look at this, daily, weekly, whatever interval you want. And then this is going to show you how much of your space is actually being used. So maybe you can cross-validate this against the survey, or maybe you only use this. But this is going to show you how your space is actually being used. And as we go from the hybrid working environment, where maybe you take a floor off an office building, or, well, it's still there, you use a floor less in an office building, over time, you can monitor how much the space is being utilized versus what you expected. And then that's really important data as you look to capacity planning and figuring out what the real estate profile needs to look like for whatever building you work in. So with this one here, this is something a lot of people are going to be looking to. A lot of people are already looking to smart building technologies like this, because the trends with commercial real estate, and I guess all real estate, and how it's going to change after the pandemic is very uncertain right now. And the smart way to do it is to use actual occupancy data to support the decisions that everyone's going to have to make as they sort of change what that real estate portfolio looks like. All right. The last thing I have is incentives and rebates. So again, going back to what I said before, smart buildings, I think sometimes immediately read that as synonymous with maybe green buildings, sustainable buildings, a LEED plaque on the outside of a building. And that's not the case, or at least it's not only the case. There's much more to it than that. And in Virginia, there are lots of different incentives and rebates available for your standard green programs, but there are also a lot of rebates and incentives that can support smart building transformations. Okay, so I've just listed a few here. I don't need to go through them, but the fact is that there's a lot of mechanisms available for people who do want to start that digital transformation and move from the sort of old way of doing things to the smarter way of doing things. And every one of the examples I covered today is something that I've personally worked on. And the return on investment, the simple payback, the net present value, they're all very positive. And in a lot of cases, these projects, like the scheduling one I spoke about, they're paying for themselves in under 3 months, which is, obviously very strong performance. And that's a combination of the energy savings and the incentive payments. And that's what the incentives are for. So I think a lot of times there are barriers to people going after using incentives and rebates, but it is worth it. You just got to put the time in up front. And I think Virginia does a great job of helping pay for smart building technologies to sort of improve the smarts of the buildings that we already have in the state. So to summarize, data is key. If there's one takeaway, smart buildings can't be smart without data, and there is no other option. And then I've just listed some of the benefits, and hopefully I was able to articulate some of those so they make better use of the systems that you already have. I think that's a great definition of doing something smartly. We're cutting back on operating expenses. They're more cyber secure. They provide better and more informed space utilization. They improve your indoor air quality, and last but by no means least, they are also much more energy efficient than a traditional building. So I appreciate everybody's attention, and if there's any questions, I'm happy to answer them.